Okay. Okay. Recap from yesterday. What we did yesterday, we discussed about scorecard. We discussed everything about the scorecard what they are also. We saw a demo yesterday, and then we went through the sample design, various issues. And then we discussed about segmentation. After that, we talked about misvalue treatment. Then we talked about outlier treatment. Then we discussed about data visualization, variable, and then we talked about weight of evidence and information value encoding, and how we go about weight of evidence trend analysis. Then we talked about correlation analysis, and then we discussed about handling data imbalance. So let me go back to the code here. We were here yesterday, and we had some data loss at this point. So I figured out that I missed some steps. Because of that, data loss was happening. So what I did is I ran it again, and data loss had disappeared. So let me go back to the where we were on the slide. You were here. We're talking about logistic regression. So let's run logistic regression here. So we have same number of observation. We lost one observation here. Rest all remains same.
I actually had one question before we proceed. So actually we tried to implement multiple algorithms here like logistic and random forest and all, and of those we saw that logistic was performing the best based on its Gini as well. So which is why we are moving forward with logistic. Is that correct?
Yes, absolutely correct. Other reason we are moving with logistic regression because we can convert the output of logistic regression only logboards to score format.
To what format?
To the credit scorecard format.
Scores.
Okay.
Scores. Yeah.
Okay. Correct.
So let's go ahead. So this is oversampling, this is oversampling, this is oversampling, this is oversampling. So let's run it. And then here we feed logistic regression or any of these. And here we basically do prediction. And based on this prediction, this value, we calculate the accuracy score, we calculate the precision score, the call score, FN score, ROC, Gini. So while this is running, if anybody has any doubt about any of these, please ask. Because there
Yeah, Nitin, so what
Yeah.
was the issue in the code which we were facing yesterday? I mean, what did you figure out?
I figured out like I ran it again and everything came perfectly. I missed out some
Sure.
steps while running it yesterday.
Oh, okay. In between, we missed out few steps. Okay.
Yeah.
So, sir, one thing like you said in logistics, because of the explainability, we get the coefficients, whereas in other machine learning algorithms like XGBoost and gradient boost, we are not able to get the coefficient. So, is it like we can't make a scorecard from those algorithms?
No, you can make a score like yesterday I had shown one demo. In that demo, I was showing three categories. Poor, average, and high. That kind of a scorecard you can make with that particular algorithm like gradient boost or random forest. So if you're mapping to few categories, easily you can make a scorecard like that. The scorecard which you saw yesterday was using gradient boost.
Okay, so sir, but when we got those probabilities from gradient boost, then how did you divide them into three categories?
I don't divide them into category. I take three outputs. Basically, it's a
Multi-label classification.
multi-level classification, which I am doing with the gradient boost.
Okay.
Yeah. So definitions are here in case somebody has. I think this is there in your code also. You can read it. If you have any doubt about ROC, accuracy, precision, I had defined them in slides also, but this is a better place to read because this is more detailed. Okay, let's see the results now again. So results are exactly same, which I got here. So if you look at these results, ROC 78 and accuracy 79. While in others, we have better result only with the support vector machine. ROC is 78 and accuracy is 79. It's exactly same result, but we can explain with logistic regression better. So there was a question that somebody asked me recently, when we can use these algorithms, like decision tree, random forest, gradient boost, support vector. We can use this in fraud applications. In the fraud, you can ensure that you get the maximum accuracy because objective is to minimize false positives. So false positive can be minimized only with the best results, which can come with any algorithm. Coming back to this one. Now we will go back and see about the ROC and other things here. So this is okay. This is our ROC. ROC is basically a gram between true positive rate and false positive rate, and it basically helps you to find out like discrimination ability of your model, which means whether you can differentiate between good and bad. That's what ROC does. While accuracy is more of like how accurate you are in terms of prediction. This is ROC, and then you have gain curve. Definition of gain is cumulative number of positive observations to the decile, total number of positive observations in the data. This we have used the library skit plot, and using this library we draw it, and it comes exactly same. Then we have confusion matrix.
So can you please explain the cumulative gains plot interpretation?
It's more of number of events up to one decile. For instance, up to this decile, you will see how many events you are getting here, and then divide by random number of random data, which will have 10% event. You could say, lift. Do you know lift curve?
No, sir.
Lift is more like cumulative gain curve only. Only thing is here you look in terms of percentile. There you look in terms of ratio. So it's more of if you make a model and you sort your data. After sorting your data into low to high probability, you will see how many events are coming in first 10 decile, second decile, 10, third decile, fourth decile, and 10 decile. And based on that, you will compare it with the random model. With the random model, you will see what percentage of events are coming it will be 10% of the total event. So based on that, you will calculate the gain. The gain is cumulative number of events up to that decile, you have a total number of positive observation in the data.
So positive here is default, right?
Positive here is default. So default up to this decile and total default. Got it?
Yes, sir.
Okay. And then you have confusion matrix. Not this one. But I have to run. Confusion matrix looks like this. So let me go back and do some explanation here. We're talking about scorecard performance. There's something called gain chart. We just saw cumulative number of project events divided by total number of events in the model. You call it depth also. So lift curve and gain charts are more or less same thing. The only thing is in one you represent a ratio, in another one you represent a percentage. Percentage, which means here you have total event in the denominator. Here you have 10% in the denominator. That's the difference between lift and gain chart. Are you understanding what I'm saying?
Nitin, I just see your slides. We're not able to see the gain or lift chart. Huh.
It's here.
Yes. Okay.
So when you talk about gain chart, it's you have cumulative number of positive observation in decile up to that decile.
Yeah.
And you have total number of default in the data. So number of default divided by total default.
Hmm.
And in case of lift, it will be number of default up to that decile divided by default in 10% of the data. So let's go to coefficients. These are coefficients. Intercept.
Sir, I have one question on confusion matrix.
Yes. Yes.
So
Sir.
I want to understand, like there is a concept known as accuracy ratio that we get from the cap curve. There is a cumulative accuracy profile. Like from the ROC curve, we get the area under the curve, right? AUC. But
Right.
there is also a concept called cap curve where we draw the cumulative number of population on the x-axis and the cumulative number of defaults on the y-axis. And we get a cap curve. From there, we get the accuracy ratio, which is basically the area between the random curve and the model curve divided by the area between the ideal curve and the random curve.
Okay. I will come to accuracy ratio in a minute. Just a minute.
Okay, sir.
So we talked about gain chart. We talked about lift. And then we talked about misclassification cost. The cost of false positive and false negative. Cost ratio is ratio of misclassifying a bad as a good to the misclassifying a good as bad. So it's a ratio of false negative. है ROC curve, you have KS, you have Gini, your accuracy ratio, precision, recall, F curve. And then there are some tests which you do when you do the rating system. On the rating system, you do the Hosmer-Longshore test, binomial test. So challenge here is whether you want to improve the accuracy or whether you want to improve the separation, which means AUC or ACR. AUC is all about discrimination between good and bad. Accuracy ratio is all about total number of events which have been predicted correctly plus total number of events which have been total number of known element we didn't predict correctly. So let me skip this one. Take you here. So accuracy is true positive and true negative divided by true positive, true negative, false positive plus false negative. This number is total events plus non-event, and this is true negative plus true positive. This is accuracy ratio. Did you understand like what you were asking about accuracy?
Yes, sir. But I have also known that there is a concept called cap curve. From there also we get one accuracy ratio.
I think it will be same accuracy ratio, but
Yes,
if you,
exactly. That was my question. I wanted to know whether those two accuracy, because there is one accuracy we get from confusion matrix, which is rightly, the formula is correct. This is what it is. But there is one accuracy ratio from the cap curve also. So I wanted to know whether both of them are equal or not.
I cannot comment because I have not worked on cap curve on this assignment, but I have seen cap curve. You can check. I'm not sure whether it has the answer, but when we talked about accuracy ratio, we talked only about this value.
And sir, what is a good threshold for application versus behavioral scorecard for this accuracy ratio?
For behavioral scorecard, you should have 75%. For application scorecard, you should have 70%.
Okay. And sir, there is also a cost ratio which you showed in previous slide, which is a ratio of misclassification in the previous slide. Yes. So is there any threshold for this as well?
I haven't worked on cost ratio, but I had done something very similar here. Like if you look here, go down further here. I have put cost of a good customer, profit from the same customer, good customer. It includes all the cost and the average the bad customer. It includes all the cost. So when you do the calculation for your profit curve, you need a cost like this one.
So how is
It
this?
includes misclassification. These are random number we have assumed, but it should come from the finance department.
Okay.
What is the profit per customer when it's a good customer? What is the loss for one customer when it's a loss customer? Okay. So let me, where I was. I was here. Let me run it. So we get rid of the offset. We already know the formula of offset, it seems. Or no, we don't know yet. So talk about lift. So when you do the scorecard performance analysis, we talk about accuracy versus AUC. We talked about KS, Gini, etc. Because the idea is you want an optimal model. At the same point of time, you want to make profit. So if you make an optimal model, you want to see whether optimal point is same point as where your profit is maximized. Because you want to avoid the false positive and false negative, especially false positive. You don't want to deny a good customer. So for that purpose, optimal cutoff is coming into picture. In some case, you compare the performance of the current scorecard versus new scorecard. So normally this data is different in the current scorecard and old scorecard. So comparison will be not apple to apple conversion comparison. So you might skip this kind of comparison, or you might make some other model using some other technique on the same data and then compare the performance. So the idea of making a champion model, which is a model on the same data, is good one. Normally it's done in many organizations. Normally this is done by the validation department. So based on the few parameters, you make sure that your model is good in accuracy. Your model can discriminate between good and bad. So those are the kind of consideration which you make when you make a scorecard. I'll give the benchmark for each of them next few slides. Then you have confusion matrix. Confusion matrix has accuracy. This is the right formula in all situations in case you are confused between cap and accurate cap and confusion matrix, because this is widely used. Then you have error rate. Error rate is 1 minus accuracy. Then you have sensitivity or recall. This is true positive divided by actual positive. You have specificity, true negative divided by actual negative. Then you have precision, this true positive divided by predicted positive. So these are formulas and these are numbers. Normally you want to maximize all of them. When you have false positive, it's type 2 error. When you have false negative, it's type 1 error. You might heard about type 1 and type 2 error.
Yes.
Okay. Then you have when you say predicted, based on the model, you will reject these ones. These are false positive. Based on model, you will reject this one. These are true positive. So ideally, you want to reduce the losses. If you want to reduce the losses, you want to maximize the true positive and sensitivity. If you want to do more business, you want to maximize the true negative and specificity. But if somebody is a good customer, you classify him as a bad customer. It's like a false positive. So you want to avoid that kind of situation because it creates customer service issue and you miss out a lot of opportunity. Any question? So this is our matrix. You look here, 263 here, and 263 here. And we have done the calculation of accuracy. Accuracy is true positive, 263, and true negative, 4886. We sum them up, divide by the total of all. And then classification rate, then we sum these two and divide by total. We call 263 divide by actual event, 263 plus 81. So you should try to do such things when you do the calculation using the code so that you understand more what actually what means.
So I have one question in this.
Sure.
If let's say I'm building an application scorecard model, or let's say my purpose is only for loan acquisition, so should I be looking at the misclassification rate or the error rate, which incorporates both the type 1 and type 2? Or is it that type 1 error would be more serious for me?
If you're making a model for, let's say, fraud management, in the fraud management, you deny a customer which is a good customer, which means you are doing a false positive thing. False positive thing you need to minimize. If a customer is a bad customer and you accept him, it's not so risky than a denying a good customer, because good customer gives you profit.
But sir, in fraud detection, though, my objective would be to minimize the frauds, right? So the second case would be more serious. Ki the person is a fraudster, but I'm accepting him as a good person.
Thing is, there is a very thin line here. Normally, you want to minimize false positive as much as possible, which means denying a good customer, because that creates serious implication on the business. You can handle somebody the false negative in terms of investigation, in terms of more work later on, but you don't want to deny a good customer, which is a false positive thing.
Okay, sir.
So let me go into the cutoff, which is very hot topic when you talk about scorecard. So there are 5 different kind of cutoffs. 2 are optimal cutoff and 3 are cutoff based on the financial performance. So where KS is maximum, at that point of time, your scorecard is doing best discrimination, or accuracy is, I would say, AUC is maximum at that point. So you want to make sure you pick that point and you find what is acceptance rate at that point, what is bad rate. Second thing which you do is like you try to find the maximum difference between true positive rate and false positive rate. And that particular point is called Jordan index. Jordan index means scorecard performance is best at this point. This is again an optimal cutoff. Then we had trade-off between acceptance rate and bad rate. Either you want to maximize the acceptance rate and keep the same bad rate, or you want to minimize the bad rate, keep the same bad rate, keep the same acceptance rate. So one of these things will go up, either this will go up, this will go up, depending upon this will go up, this will remain same, or this will remain same, this will go down. So one of the strategy which you will choose depending upon the management decision. Then fourth cutoff is profit curve, where profit is maximum. So you will get these numbers: cost of misclassifying and cost of having a good customer, cost of having a bad customer. So you do all those calculations and you figure out what is the profit at each acceptance rate. And based on that particular acceptance rate, you will decide whether this is a good profit for me. And then fifth one is expected loss curve. You might heard about PD, LGD, and EAD. So you need to do that calculation to find the expected loss. Where expected loss is minimum, you want to pick that point. Let's go to further slides. So this is our ROC. false positive rate and true positive rate. And this is cutoff calculation here. You want to maximize the difference between true positive and false positive. You sort it. After sorting it, you figure out the maximum point. It comes 0.509. Same thing you do using different logic, and you again find the same value. So this is your optimal cutoff based on the ROC. Then we have optimal cutoff based on the KS. I have used this particular function from this library to plot it. This is again 5.11. Normally, this value from the KS and this value from the ROC, they should be very similar value. If these are very similar value, it means your model is consistent. And this is done with the hand when you create the decile. 10 decile were created. Again, we are getting the value 0.516. In second decile, where KS is maximum. Here, KS is 57.3. But when you do with hand, it's 50.6. These two are different values. This calculation way is different. Here you do row wise. Here you do decile wise. Any question? Then we have cutoff based on the acceptance rate and strategy curve and the bad rate. The plot between acceptance rate and bad rate is called strategy curve. This one I had taken from Bart Parsons' note, and he has put this kind of point. He said either you can keep the acceptance rate low, reduce the bad rate, which is 0.02, or you can increase the acceptance rate and compromise with bad rate. So there are 3 points here: 80%, 90%, 95%. So all this will be put forward to the management. Management will make a mind what they want to do. Then we have profit curve. Yeah. Yes, please.
Hi, Nitin. I just have one question. So, while deciding the cutoff strategy, why are we not incorporating important metrics like NCL and ROC into the picture? Because at the end, everything has to be bring down to rupee value.
You mean we should put in terms of numbers?
Net credit loss.
Yeah, we are coming there. We are going there. We are going there. So here profit, and we see profit is going to get stabilized here. After it's going to get down. Approximately at 95%, the profit is going down, which means you will not go beyond 95%. Then you have expected loss. So this 1, 2, 3 multiplied by this value. And we start seeing there at 80% it's point, at 80% this is this one. And at this point around 95% it starts going down sharply like a linear line. So you will stop here. So based on this 3 curve, expected loss, profit curve, strategy curve, you want to have cutoff of 95%. But based on this one, optimal, you want to figure out what is the acceptance rate. So let's go here, the code. Let me run this, otherwise it creates problem later on. There's something called neutral score. Neutral score is a score beyond which if some variable has a score, then particular thing goes into the region for rejection. For instance, you have these variables, and if any variable score below neutral score, that particular variable will be region of rejection when you reject a customer. So you calculate neutral score. At neutral score, your weight of, you keep all the coefficients 0. You look this formula here, the score formula. So coefficient, if you put 0, it will become offset minus by n minus factor into intercept by n. This is what it is. This is your neutral score.
Can you hello?
Yeah, neutral score is a score at which all coefficients are 0.
Can you like repeat the conversion of scores into, I mean, probability into scores, like the offset thing, the top, the cell number 118, I guess,
1 9.
which has the PDO and the factor formula and everything.
This one,
Yeah, block number 118.
119, 118. This one.
Yeah, the score
Oh.
wherein we are converting the.
This is
Yeah. Yes.
this
yes.
is this is the
100,
PD.
119.
Yeah. So this is intercept. This is coefficient. So you are dividing 20 by log of 2. Log 2. So when you divide it, you get the value of factor. From the factor, you will calculate the offset, because you are taking that at 600 point, your log, you have
PDO,
odds,
right?
yeah, you have odds of 50 to 1. But once you increase the point by 20, your odds become 100 to 1. So when your odds become 100 to 1, it means it's 2 times at 20 point.
Sir, but how are we going to know this in advance when we are building a scorecard? Like, what would be the PDO and what is
PDOs and score are provided by management to you, that you want score in this range. For instance, I can change the score range here, but it is through my code. But it has to be provided by management. They want the score to be in this range.
like, what is the role of PDO? We have initially we will know an odds ratio at some score. Like you have written 50s to 1 at 600 points.
Yeah, let me go into theory more, then we'll go into this one. 1 minute. Okay.
Okay.
Yeah. So let me cover theory first. So I talked about lift chart. In the lift chart, at 10 percentile, at first decile, you will see how much lift you got. That value of lift is your lift of the lift curve. So you will sort the data from lowest to highest. After that, you will see how many events are coming in lowest in the first 10 decile, first decile. And then you divide that particular value by the random data, like it will have 10% and 10% event. So cumulative number of positive up to the decile using the model how many number of positive up to the decile if I use a random model. When you say using the random model, it means there is no model. When you say you are talking about model, you're talking about probabilities. You sort it by probabilities and see how many events are coming on the numerator and how many events are coming in the denominator. And you plot it like this. In case you are confused, please read and I will answer your question if you have a question. If you read this part from here to here, it will be clear. Is this clear? It's more like how much lift you are getting by using the model. What percentage of event you are getting in the first decile by using the model divided by what percentage of event you are getting without using the model. It is clear?
Yeah.
Then we talked about gain chart. And then there's something called gain table. Gain table is a table which is the master table for all the cutoff analysis. Here you will have approval rate, rejection rate, profit, loss, net profit, false positive rate, true positive rate, how many approved. So this analysis is done in gain table. Then there is something called out of time validation. Out of time validation means there's some data which basically is not in the same period as your sample data. Using that data, you do the validation, and that validation is called out of time validation. If you're making model between 2016 to 2018, then you will take data from 2018 to 2019 for validation. That's out of time validation. Or you will take the data before this particular period, like 2015 to 2016. That's out of time validation. You want to check all the quantitative and qualitative measures, and you want to make the comparison of the statics with as far as development sample is concerned, as far as out of time is concerned. And you compare the performance across different periods to make sure your model is robust. Any question?
No.
Okay. So when you do the comparison, you want to look at the all metrics, which could be ROC, which could be KS, which could be Gini, which could be fish static, which could be parameter estimate, whether parameter estimates are similar, PSI, PSI, and business performance. So you compare all those things on out of time sample with development sample to do the out of time validation. There are 1 minute. There are times when a scorecard does not validate. There are a couple of reasons for that. One reason could be you have very few variable in the data in the model. Another one is there is a concentration of certain type of attribute in the one sample. For instance, you have people who are very old in age and in the sample, or you have people who are very young in age in the sample. So if you have this kind of problem, not a heterogeneous sample, your model will not validate. or your development sample could be from non-normal time period. For instance, you took a corona time sample and you build a model on it and you try to do validation of that particular model. If you did not validate or you not apply the exclusion correctly or model is overfitting. So all those are the regions that your model will not validate. If your model is not validating, then you need to build new model or you need to rebuild the current model so that it gets validated and you use more variable in that. So when you build a scorecard, you want to make sure you have most comprehensive risk profile with as many independent data items as possible. And it's interpretable. It can be implemented by the IT and operation department. And it basically supports the view 360 view of the department, which means marketing, operation, IT, and customers. So everyone is taken care when you build the scorecard. When you use the risk profile basically help you to make sure there is no population shift. Quality of the applicant is very good. And you can set the limit. You can do the pricing. So everything you can do when you do the risk profiling. Risk profiling means you have a comprehensive list of variables in the model which are balanced, just like this. It has nearly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 variables. What name Siddiqui says, your model should have 8 to 15 variables. If you have more than 15 variables, then it leads to overfitting. So risk profiling it should be between 8 to 15 variables. And when you have risk profile for a scorecard, it's more likely to be stable. If one variable goes wrong, it does not make the whole scorecard unstable. It basically will add this with some other variable. Anybody any question on risk profile? Now we talk about scaling. So why we need to do the scaling? Scaling is to do the software limitation because you cannot work with the probability. You want to have continuous scores. Yes.
Yeah.
And then it's very easy to understand, easy to interpret, and there is continuity. There are homogeneous group of variables which are mapped to a score. So there's a continuity. It satisfies the legal requirement and scaling components are easy to define. So you define odds at a score, then you define point to double the odds or triple the odds, and then you calculate the PTO. For instance, in this scorecard, you have age, time at residence, region, inquiry last 6 months, delinquency during, residence burden. At 300 point, you have odds 30. At 320, you have odds 60. At 340, you have odds 120. So, good example of video is this. At 600 point, I have odds of 4. At 620 point, I have odds of 8. My odds are doubled when I move from 600 to 620. So PDO will be 20 divided by log odds 2. I think you know all these things, right?
And not most of us, but
Yeah. So let's say score is offset plus factor into log odds at which you want to fix a score and score at that point, and then you have PDO. If you have all these three values, then you can calculate the score. Score is equal to odd plus factor into log odds. Score plus PDO into log offset plus factor into log odd 2 times odd. So when you solve this equation, this and this, you will reach here. PDO is equal to factor into log 2. Factor is equal to PDO into log 2.
PDO by log.
Point to double the odds. So this is how it is sold here. This is what information is coming from the management.
But sir, like how can you help us explain how the management would decide this 20 PDO?
Management will basically thing is this probability is mapped to a score, and this is a tested method where you can define like I want it to be 800 or I want it to be 900, I want it to be 400, depending upon the country, depending upon the range of the score in that country, you will make this decision. For instance, in UK, score range from 300 to 900 something. So you will make a call that scores are falling in that range if UK scorecard is made. Same way in US, I think score range something else. I think they range from 200 to 600. I'm not sure, but then you will make different assumption about the PDO and odds. So depending upon the country, you will make a decision where you want your score to fall for good customer, for the poor customer. Make sense?
Yes, sir. Thank
Okay.
you.
Nitin, I have a question here. So, like,
Yeah.
if I need to understand the first statement, like odds of 50 is to 1 at 600 at 20 PDO.
Yeah.
So when my score goes from 600 to 620, my odds from 50 is to 1 increases to 100, right?
Right.
Okay. Okay.
That's what it means.
Hmm.
Odds means ratio of the probability.
Probabilities. That I got. Also.
Ratio of probability divided by ratio divided by 1 minus probability.
Mhm.
So all this calculation which you did there to calculate that logistic regression, it's giving you a probability.
Yeah, yeah. So
Sir?
offset is.
Yeah. Interesting.
Yes, please.
So, sir, here the log odds can also be replaced with the WOE, right?
It's a good question. The calculation is very similar, but it's not done.
Okay.
Yeah.
Like the only reason we are calculating the WOEs and replacing those with the actual scores of a variable is because in the end, if we want to get the score, so we will be using that WOE values.
Right. Thing is, you reach to the score using this equation. And if you want to reverse back to the probability, then you will use this formula from the score to the probability.
Yes. So, sir, like if we only want to build a PD model, probability of default model, then we don't have to do the weight of evidence transformation of the variables. We can just use the raw values and then get the PD model.
It's possible, but in practice, where I have worked, most of the places they had a weight of evidence transformation.
Yeah, most of the places they use WE.
But then, if they are stopping at a PD model only and not converting the PDs into scores, is it beneficial to you do the weight of evidence transformation?
It gives the stability to your model, because when you create attribute out of a variable, like we have created 10 attributes yesterday. For instance, if I go here, uh, so I have created these many attributes here from this variable. Each attribute is a homogeneous. So when you have homogeneous attribute in one variable, your score will be stable. It will not be affected by outliers within that range.
Okay. So like, so sir, you are saying that even if you want to build a scorecard or a PD model, the initial steps can be replicated for both, like WOE transformation can be used for both.
It has to be done this way to make your model stable.
Okay. Thank
Yeah,
you.
yeah. So we have this equation. Score is equal to factor
Of
into odd
of
plus offset.
offset plus,
Yeah. So same equation you have here. So you are bringing it down to this level. One more thing, which basically I wanted to tell you, which I figure out, that initial sign here is positive for low odds, but cat sign is negative. The reason for sign being negative is uh, you are calculating probability like P, but here when you do the score, when there is a good score, you want customer to accept, which means low probability. So probability has to be reversed, or low odd has to be reversed, or like 1 minus P divided by P. You're getting my point?
can you repeat once again?
Thing is, when you want a score, higher score means good score.
Mm-hmm.
Same point of time when you have probability,
Mm-hmm.
probability means high probability means bad customer.
Bad customer. Yeah.
When the good score means high
Low
score,
probability.
good customer. So probability and score are having negative kind of relation.
Yeah, inverse relationship. Yes, yes.
So because of that, odd has to be reversed here into negative sign,
Oh,
so that so that basically you make that adjustment, score comes.
Mm-hmm.
Okay.
Yeah.
So beta is a regression coefficient here.
Mm-hmm.
Weight of evidence is weight of evidence of that attribute. This one. Number of characteristics in the model n. Intercept regression. This one. Number of groups in each characteristic k. So for each variable, we need to do this calculation and sum that up. And let's talk about neutral score.
Mm-hmm.
Neutral score is a score where all the weight of evidence value is 0. If you put it 0, it will become offset by n minus factor into a by n. This term will become 0. Right?
Yeah.
Sir,
So
in the previous equation, why the A has been divided by N?
because you're
Each
taking it from the outside 1 to n.
Like in the first step to the second step?
Thing is, initially age outside.
Okay, got it.
Yeah. So neutral score, if variable has a score which is less than neutral score, then it would be region for rejection for that particular customer. For each variable, you need to get a score which is higher than neutral score. Then only you will get the credit. Are you getting my point? You have 9 variables like LTV, age, or delinquency, or something else. Then you want to make sure that you score on each point above the neutral score. If anyone has a neutral score less than, if any variable has a score less than neutral score, then particular applicant will be rejected because of that reason. And that reason you will specify in the scorecard that this is why I have rejected this particular customer.
It's kind of a
Yeah.
baseline score, right? Like
Yes,
anything below that should be rejected.
exactly.
So can you please explain this again? Like I'm not sure this neutral score, and then how do we decide acceptance and rejection of customer based on this?
Thing is, I was here. This is my neutral score, 52. If any variable has a value score 52 or less, 52 less than 52, that variable will basically region of rejection for that particular customer, and you will can specify to the management this is why this customer was rejected. Is this okay?
Okay, so I got it. Thank you.
What is this weight column here, Nitin? Like in the table, the last column weight. So what does it signify?
Uh, this particular thing I wanted to remove, but I had left it. I'm not.
Okay, okay,
Yeah,
okay.
yeah. But this is how mapping is done from weight of evidence to score. For
Hmm.
instance, we go here in our, where was our,
Hmm.
And this neutral score serves as a rejection score as well, that if the score is lesser, so the application would be rejected.
right.
Okay.
So this is example of score. So each attribute is mapped to one score using that particular formula which you just saw. So if somebody has a delinquency between 1.99 to 4, he'll get this score. Somebody has a delinquency between 4 to 5, he'll get this score. If you get 5 to 6, he'll get this score. Same way, like income between this range, you'll get this score. And this is minus. You have this
Then
range,
can you score a little right? Uh,
right?
uh, uh, mm, score. Yeah,
So you could say
got it, got it.
you have very easy mapping from your weight of evidence to the score. This is advantage of using the weight of evidence. And this score can be mapped to the probability also, total score, by using that
Hmm.
particular formula, which we just saw here, this one. So this is example of point allocation. And then we go to the scorecard scaling. So let me go back here. We have run this one, uh, okay. So this is how we calculate the scores. If anybody is not clear, please ask. Calculation is happening, it's done. And we assign this as a score. And we can see this particular data. Here, this many values of the score. You can see the head of that particular data set. So we have a score here for each customer.
So, I had a question here.
Yeah.
So now each variable will have a different weight of evidence, right? And
Yes.
each and it will be grouped by different weight of evidences, like from range something to something, there will be a number assigned. There will be a neutral number at weight. There will be a negative number after that. So total, like in this conversion, we don't decide that okay, there is a salary or last average balance factor should have some points allocated, like 150 points. So that is already taken care by this weight of evidence.
Yes.
That okay. Now it is more clear. Like I was just thinking that how do we decide that this particular variable should have a higher range of
that particular thing is decided by coefficient.
coefficients. Yes.
Because if you look at this here, you will have coefficient, and then you will have weight of evidence value.
Okay. Yes. Yeah, thanks a lot.
Okay. So we will see the distribution, how the distribution look like. So we have very few customers who have low score. Our maximum customer has good score. This is why we have less number of default in the data. So it's making sense in terms of business, right? Like very few customers are having low score here. Most of them have a good score, about 450. Minimum score is 361. Maximum score is 611. So depending upon that particular value of PDO, odds, and score, you will have this kind of range which we have here. Okay, let's plot lift curve.
Nitin, if you don't mind, can you go to that Excel sheet again, please?
Yeah, sure. Yes, please.
This one. I mean, just out of curiosity, just scroll, go to the first column. The variable is month since last delinquency, right? The very first variable on top.
Yeah.
So okay, 4 से 5 5 से 6. So ideally our score should improve, no? But we see a break, like if you look at row number 2 and 3, 45, 43. So
Thing
ideally
is,
the score should improve, right? Because higher
Yeah,
the months we are since delinquency, the score should be higher for that customer, right?
yeah, you are right about that. I'm totally with you. The
No, but
reason,
yeah, I'm just asking out of curiosity. Yeah.
yeah, it's a good question. Normally score is going up, but these two buckets,
Exactly.
they need to be merged.
Yeah, of course. Yes.
I think I spoke about it yesterday. If you
Yeah,
can
yeah,
get
no,
into it.
yeah. Yes.
Okay.
ठीक है. Okay, thank you.
Also, sir, like one thing, this score formula, this PDO offset formula, it can only be used for logistic regression, right?
I will investigate and come back. At the moment, that's what I know.
Because sir, like I have seen clients calculating WOE for advanced ML also, like gradient boost, random forest. But then how do they come up with those scores? Because in the formula you showed that WOE is used. But then along with that, the coefficient is also there. But then for random forest, we don't get coefficients.
For random forest, we don't get coefficient. For gradient boost, also we don't get coefficient. So
Yes,
we
so
get so
yeah.
the problem. This is the problem.
But then I have seen for random forest scores getting generated. Now I'm thinking how they must have got the scores.
Thing is, inside the model, uh, uh, inside the random forest, there are a lot of trees, and subset of trees used for the calculation. So even if there are categorical variables, it does not matter. Even if there are outliers, it does not matter. So it maps to certain classes based on certain values. So if you have some values like X, Y, Z, based on that it will do the mapping, but it will not tell you what is the score. So classification will happen, but you will not know what is the actual value of this particular score is. This is the problem which we have.
Okay, sir.
Yeah.
Thank you.
So we have reached till here, and I will just show this one recently. Now we talk about PSI and CSI. Let me first complete the lift chart here. I think you can use all these macros which are there as it is. This is lift. You look at this point here. Lift is approximately 5 point something, which will say 5. And this is how, okay, let me get into this particular piece of code which we used for calculation of cutoff. So we have taken this threshold, FPR, EPR from here, okay, from the ROC. And then we have used it here. Created a data frame. After creating a data frame, we have taken the valid data set. We have put that as a Y valid, and then this probability, and this loan balance. Loan balance we are saving from the beginning, and this balance will be used to calculate the EAD. So this is minimum value of the threshold. And we have written small function, one for calculation approved, one for calculation of bad rate, one calculation of EAD. We calculate using this particular N approved, how many approved are there. Then we calculate how many rejected are there. What is the bad rate using the bad rate function. and we calculate the approval rate and rejection rate. Here we have taken these two values, like good customer is giving a profit of 50. This number will come from the finance. Bad customer will give us loss of $200. This number will again come from the finance. So we calculate how many good customer we have using this particular formula. 1 minus bad rate multiplied by approved. And this loss using this particular formula, how many bad customers we have. And we calculate profit and loss, and then we calculate the net profit here. For EAD, we have assumed EAD LGD of 1. And EAD, we calculate how much loan balance we have for that particular approval rate. And then we have bad rate multiplied by bad rate is PD. Multiply by LGD, multiply by EAD, we get the expected loss. And this is the calculation which is shown here. Let me run it. So this has come up, full table. This table is called gain table or gain chart. And this is calculation of cutoff, which basically I was showing you. 0.51, another code, same calculation. And we plot the strategy curve between approval rate and bad rate. Let's plot it. This is how it's plotted. And then we have plot for the profit curve, which we just saw. This is profit curve. This is expected loss curve. At this point, there is sharp increase in expected loss. And then we have KS. This KS code is here. This is KS plot. And this will come using this particular calculation, which is done here. This particular piece of code. Okay. And you want to figure out at what score and what acceptance rate you're getting the optimal cutoff. To calculate that, we use AS2 sample. It will give us the probability, at which probability we're getting the cutoff. And using this particular table which we have plotted before, we will find out what is the acceptance rate, which is 77.6%. Are you following, or I'm just doing?
Sir, in like practical applications, which out of the so many cutoff determination methods you have shown is used most widely?
Most likely, I will go with the optimal cutoff when it comes to the fraud application or medical application or cancer application or something else where I need optimal thing. Because I want to make sure that my false positive and false negative are minimized. When it comes to the granting credit for the financial purpose, then I will use the acceptance rate and bad rate values because I want to maximize the profit. So objective will be totally subjective and it will depend on the industry where you're using it. Where objective is like you want best performance of the model, you will go with the optimal cutoff. Where you want financial performance, you will go with the acceptances and bad rate or expected loss or profit curve.
Also, sir, one more question I had on confusion matrix is that at what threshold are we calculating confusion matrix? Like, are we always taking it as 0.5?
No,
Then it depends on, let's say, if the client has already provided you an accept reject threshold for the scorecard, so we should ideally calculate at that score.
I like your question very much. This is a very good question. Where optimal performance you are getting, like you're getting the optimal performance at this point. This point,
Hmm.
this
Yes,
this
sir.
point,
Like how to choose. Like we can choose any one and then calculate the confusion matrix at that threshold.
yes.
Okay. But sir, like one common criticism I have found with this approach is that they say ki, let's say if we have chosen a cutoff, let's say it comes out to be optimal cutoff, let's say it comes out to be 0.6 probability. So we will say ki, if the probability is more than 0.6, we will predict the borrower is a defaulter, and if the probability is less than 0.6, we will say that the model is predicting him as a good borrower.
Yes.
Now the thing is ki, like if that threshold has come is like an accept reject threshold for the scorecard. So they say ki if the borrower is getting rejected at zero point 0.6, that doesn't mean that he has a sure shot probability of default. It can be that the borrower is rejected, but later it comes to be known that he was a good borrower. Like we are kind of mixing the two things when we say ki we already have a threshold, but then we are using that threshold to say that all the borrowers above that threshold are predicted as defaulter, even though those are reject borrowers from the scorecard.
Thing is, it can quite happen that you reject a customer. He goes somewhere else.
Hmm.
After going somewhere else, he behaves nicely, and after behaving nicely, he become a good customer. But since you have a scorecard, which is very much particular to your company, and you want to say that based on my criteria, I reject it. It's more like matchmaking. You would say that you have certain requirements. Based on those requirements, you have rejected someone,
Hmm.
and then he goes to someone else, and she has different requirements, and then based on her criteria, it matches to her. She get interested, and it become a good customer.
Yes.
So it's a more or less same thing.
So it's like for us, so we are tagging him as a predicted defaulter, even though in actual he got some loan elsewhere and was a good borrower. So are you saying that this is not a serious problem, like to think about on this?
Thing is, when you get 100 customers, and your scorecard says that based on this 10 variable score, I find he is a risky customer. I don't want him to allow. So then it will go to the management. Management will look at the override score. If override score is again he's scoring less than override score, then he will be rejected. So it's not just a scorecard; it's a overriding also happens. Overriding means like somebody should get 420, but he got 410. Then it will go for a overriding. They will check whether he does not have bankruptcy, he does not have any default, why he is scoring less. If they find reasonable value, then they will accept him, they will give him the credit. But they are selecting out of 100, 10 or 20 customers based on override. Ideally, override rate should not be more than 5%.
Yes, yes. Mm. So there are two concepts of overrides, right? Within high score overrides and low score overrides.
Right.
So this example was, I think, low score overrides, wherein you accept someone who has a low score, and
Yes.
you also reject few customers who would have a high score, but due to some overrides policies and some internal policies, you reject him or her.
Right.
So, like the conclusion would be, sir, ki we can calculate the confusion matrix at the cutoff which is provided to us by the client, and it is not so serious ki it turned out that the rejected person came out to be predicted as a good borrower somewhere else or in actual.
Thing is, as far as you are concerned only about your scorecard because your scorecard is based on the past behavior of the customer which came to you. You don't want to go and think about some other bank because they might have different criteria.
So it's actually a very subjective thing. So depends on the risk appetite and framework of an individual bank or financial institution, which may vary
Right.
bank to bank and institution to institution.
Right.
Okay,
So as
thank
per
you.
Rizima's example, if a customer is rejected at, let's say, HDFC Bank and or an XYZ bank, he might get accepted at ABC Bank. So there could be possibilities where the rate of interest would be higher than the first bank, even if he's accepted. So like there are a lot of things coming into the picture. So it's just not like a model. So obviously management has to decide the risk framework, whatever we have, the appetite, and all those things. So like building a model is, Nitin, I think, very first step, but the final thing is management and the strategy team, they decide what they need to do.
Exactly.
Yeah.
Okay, sir, thank you. Yeah, thank
Welcome.
you.
Okay. So we're getting the probability. Sorry, we already done this. Let me do it again. And then we're getting the acceptance rate as an acceptance score. This is the maximum minimum score. Maximum KS cutoff. Yeah, this is KS cutoff. Then we do again. And here we are calculating the score for each variable and its attributes in this code. I written this code. This is not very great code, but it's working. And then we talk about PSI and CSI. Let's talk about it here. PSI and CSI is part of the front end report. With the front end report means like if I maximize it, it's more like you divide your population into 10 deciles and you have development data, you have current data on which you are going to work. And you calculate the percentage of the development here, then you calculate the percentage of development current here. So we have put 1, 2, 3, 4, 5, 6 number. Then we basically subtract from the 5, 4, and then we divide 5 by 4, and then we multiply 6 and 7. We multiply, sorry, 8 and 6. 8 and 6. It gives us an index. And this index is called population stability index or score stability index. It's a measure how population is similar to the current population, development population. So always going to compare with the development sample. We're not going to look at any other data when it comes to comparison. In our case, we had done this calculation. We got 0.17 value for the PSI, and this is our map for different category. I had done it for probability, because probability is also a score. And this is the criteria. So based on this criteria, our model is not very stable, it's a stable model. Because we got 0.18 value. If you're getting value over 0.25, in that case, you need to rethink whether model is good or not. Normally, these reports are run 3 months, 6 months after the model is built and is used. These are called front-end reports. So there could be very few reasons for being model unstable. Either applicant profile has changed. For instance, it could be demographic change, it could be some other change, or some marketing campaign has run, or some competition has come up, or some product change happened, some regulatory change happened, some loyalty program has been done, some government scheme has come up, some festival is going on, or some customer has changed their preference, or economic cycle basically has come into recession or upturn, or it could be mistake in the data or coding error, something like that. So all these could be possible reasons for having a unstable result from the PSI. So when you get result from the PSI, which is greater than 0.25, you want to do the root cause analysis. Do the root cause analysis, you will try to figure out which variable is responsible for this problem. So this particular analysis is called characteristic stability index. Characteristic analysis to detect the shift in the scorecard characteristic or variable or model or input. Or you might want to figure out some of the non-scorecard variable to point out it could be the reason. These variables should be very strong, but not in the scorecard. For instance, age and time at address. You want to investigate if you see there is a problem with the age, you want to see time at address also. This kind of analysis need to be done. You need to look at the numerator and denominator of the index, which is misbehaving, and you want to
Can
collect.
you
Yeah.
explain this second point? Shifts in non-scorecard characteristic.
Thing is, as far as my scorecard is concerned, I'm talking about only 9 variables now.
Yeah.
But I have one more variable, which is very similar to bureau score, let's say.
Which was not included in the model, right?
Which was not included in the model. Or debt ratio, which is very similar to income. Or arrears, something else, or something to do with delinquency, another variable. So we need to analyze those variables which are very similar in nature to our variable in the model.
So, okay.
Is this clear? Okay. So this report basically compare development versus current sample. And there are two kind of shift I'll explain. One is shift in index because of variable, one is shift in the point. So let's say this is for income. This is development sample, this is current sample, this is development percentage, this is current percentage. You subtract from 5 to 4 to get the change. Divide by 5 to 4, you calculate the ratio. You calculate the log of this particular one, you get 0.12. you multiply by this value by this, you get a value here. This is contribution to index. On the other side, if you multiply 6 difference by the point for that particular attribute, you will get a score. So catch is either you are differing on the score or differing on the index. You need to calculate both. Are you with me?
Yeah.
Anyone, any question?
Sir, I have one question. Like in the code which we saw yesterday, I think the highest Gini was coming from the undivided segment, right? Where we use the raw values for the variables.
Yes, but when we use the WE value, we are getting better Gini than row variable.
Okay, so then it is fine because otherwise, sir, if raw variables are giving better Gini, then this analysis of PSI won't really matter because then we are using raw values.
No, we will not use raw values because of the stability issue in the model. We will use WE values. Anywhere I worked, I saw WE value being used.
Okay, okay, sir.
This is our calculation of different variable. So we have this variable which has maximum point 0.13. Then we have another variable annual income which has 0.627 or 0.11. Ideally, you want it to be less than 0.1.
Point. Like maximum should be 0.25, right? Same as PSI.
Okay, okay, agree with you. So let's talk about reports. There's something called override report. Let me run the rest of the code before I get there. So this is population stability code here. And this is how we calculate the population stability. 0.18. And then we are looking at this column. This is for calculating CSI. This is here. This is the index one. Okay. This is index one. This is all index one. But points I have calculated somewhere here, which I was showing you just now. These are the points calculation. Points and index are different. As far as index is concerned, it should not be over 0.25, but points will be subject to PDO, score, and log odds value. So based on that, you will decide the cutoff for the PDO for this particular one point. So I was talking about these are points, these are index. Are you following me?
Yeah.
So here we have calculated the point values. Here we calculated the index values. This is the index values. So two different things which you need to calculate. Okay, before I get into rejected inference, let me cover some theory. So there are two kinds of override: lower side override, higher side override. In the lower side override, you approve a low score, fail score. In the higher side override, you reject a higher score because of policy rule. For instance, here, this is lower side, this is higher side. On the lower side, these are approved. These are approved. On higher side, these are rejected. So lower side, we are accepting 4.84. On high side, we are rejecting 9.8909. This is from name Siddiqui, you can create this one. These are reports which are not immediate requirement, but if you are getting into monitoring and validation, then you need to do it. This is another way or representing override report where there is something called system decline, system accept, manual decline, manual accept. On the low side, 34 has been declined, they have been accepted manually. On the higher side, system has declined 125, but you have accepted manually 5. 102 have been accepted by the system, but they have been declined manually. 200 have been accepted by the customer, but they have been declined by the manual. So these are different reasons why you want to reject on the higher side. These are different reasons why you want to accept on the low side.
So what is derogatory?
Derogatory means either somebody has lost a job or somebody basically spending too much, and you know that particular thing that he basically getting into financial trouble.
Okay.
So when you talk about override, you need to always specify the region. It could be system region, it could be manual region. For quality purpose, you want to ensure that there is an acceptable override rate depending upon the type of product. For credit card, this override rate is 5%. For mortgage, commercial, and other loans, there will be higher override rate which will be acceptable. But there is a regulatory requirement that there should not be too high override rate. If you have too many override region, then they should be ranked. Based on that, you will decide that this is the best region to override this particular customer. On higher side, you will find the most negative region to reject. On the lower side, you will find a stronger region to accept. Any question? There's something called delinquency performance report. So delinquency performance report, again, this is from name Siddiqui. So you classify all the accounts in the score range. You see how many are active, how many are current, how many go into this particular bucket, how many go into this bucket, how many go into this bucket, how many go into this bucket, how many have been written off, how many have been bankrupt. So this analysis needs to be done on each score range. And then you need to see whether scorecard is doing the good job or not. To see whether scorecard is doing the good job or not, it is something called scorecard accuracy report. So you are expecting here 23% bad, but you're 18% bad. 18% bad here, you're getting 12% bad here. So if there's too much, if this rank ordering is not happening here, rank ordering is not happening here, then you might see that this scorecard is not working. Other thing, there should be not too much difference between expected and actual. Make sense? If anybody want to ask any question, please ask. I can answer now. Then there is something called vintage analysis. Vintage analysis means you do this analysis, how many delinquency you are getting from the each quarter, and analyze where the sample is coming different. For instance, April 2003 is a bad sample where basically in second quarter you got 60.65% delinquency. Here you got so many delinquency. So you keep on doing this kind of analysis to figure out where sample is not normal. If you find out sample is not normal in a lot of places, then also you need to rebuild the scorecard, which means scorecard is not working.
So this is cumulative bad rate.
Yes.
So this is an analysis we do after we have built the scorecard.
It's normally after, it could be monthly initially. When model is stable, you do quarterly. When model is more stable, you can do it biannually.
Okay.
So vintage analysis compares the bad rate for different cohort which are opened in the same month or same quarter. When there's a high risk quarter, high risk cohort are there, you need to find out the reason why this particular cohort has been risky. If you can't figure out the reason of why this particular cohort is risky, then probably you need to do more analysis to figure out what's wrong with the scorecard. If the scorecard is doing the good classification, you should not get that kind of delinquency in the second quarter.
So like I have a question on that only. Like what is the issue with the bad rates are not that high, right?
Bad rate, I would say 1% is higher. It's almost closing to 1% here.
So like for smaller time periods like month on month, quarter on quarter, if the bad rates are significant, like it's a jump of around 1%, then it's you are saying that it's not, the model is not performing well.
Normally, it should have a expected range like this one. In each score, you would have expected bad range. If expected bad range is crossed, in that situation, you will have this kind of situation.
So how are we getting the expected bad rate? Like for each of the decile or the score range, we have a bad rate that is coming from the model.
That is coming from the acceptance rate.
Okay, that is the actual bad rate and expected is from the model.
Yes.
Okay.
This is acceptance rate, and you are expecting the bad rate distribution be like this.
Okay, and then how are we comparing this with the vintage analysis bad numbers?
In the vintage analysis, if these numbers are too different, these two numbers, then people will show this kind of highs. If this high is repeated many places, then you will worry. But if happening once, then you will not worry. You will say there is some seasonality issue in the March April.
Okay. Okay, sir. Thank you.
So let's talk about reject inference. Reject inference is all about having, like you have accepted, you have rejected customer, then you have offered declined customer, intermediate, indeterminate. So you will not worry about this one. You will worry about these two. This is your door-to-door population, which you have basically accepted or rejected. So when you build a model, you want to make sure that you make a model on through-the-door population. To ensure that you make a model on through-the-door population, you first make a scorecard on the accepted, and then you include this rejected in your scorecard in such a way that it gives good value, or what to say, good value for your score. Let's say here I have this many rejected, I have this many accepted. Out of that, this many turns out to be 914 bad, and this many turns out to be good. Here, this many turn out to be bad, this many turn out to be good. So if you look at the ratio of good is more here compared to here. Are you with me? One has bad rate of 33.98, another one has bad rate of 12.8. So because of bad rate, quality here is good and quality here is bad. So once you see the bad rate is 30.98, you'll be very happy that you rejected them. But you want to make sure give them consideration while making the model. So this is the picture which I had discussed before. Does anybody want to explain this again? Excuse me? Anyone? So you had data, you clean the data, you make a scorecard on non good, bad. Not good, bad means accepted customers. And after making that scorecard, you implement the reject inference. After implementing the reject inference, your data will basically have accepted data plus rejected data. And then you will make a scorecard again. That scorecard is finally scorecard. You will validate the scorecard. This scorecard process is called application scorecard process. So when you look at this old scorecard, you have proved this many, and you have known good, known bad. You have declined so many. Out of that, you infer good, infer bad. This information can come from the bureau. In case you don't have the information from the bureau, then you have to use reject inference technique. That reject inference technique I will explain in next few slides. Does everybody understand this?
So in making every scorecard, we have to include the reject inference.
In case you are using in case you are making a scorecard for through the door customer, which are new customer,
Okay.
you have to do it.
Okay.
So here, inferring the rejected means predicting unknown, predicting the unknown, and then after predicting the unknown, you will combine that with the original data, and you will make a scorecard again, the same process. If you can remove the bias with the judgmental correction, then you don't need to do reject inference if you don't have that data. But in case you cannot remove by judgment correction the bias, in that situation, you need to do the reject inference. So there are few techniques. I will explain only three. One is hard cutoff.
Sir, can you please explain the bias again that is there for which we need to do the reject inference?
Thing is, in case there is a bias, which means you have 100 customer came to you. Out of 100, you accepted 80. You got a history of 80, but 20 customer have been rejected. But you don't have any history. You make your initial model on the 80 customer. After making the model on 80 customer, you want to include that 20 also in the model by some means. By some means reject inference, which means you'll make a prediction out of 20, how many are good, how many are bad. And that is called inference. This is how bias is removed.
Okay, sir, thank you.
So you will make a model, you will set a cutoff of the probability to assign a class. Above this probability, people are bad. Below this probability, people are good. And then you combine that reject with good bad model and make a model again. And this is very simple and very easy to do. Second technique is parceling. In the parceling, you will basically have this kind of data, good and bad data for the accepted customer, and you reject data here. In the reject data, you will infer how many are rejected bad, how many are rejected good. So if you sum these two, you'll get this number. If you sum these two, you'll get this number. Normally, you want to take the bad rate, ratio of good and bad, multiply by it a factor, and that factor will help you in calculating what percentage of reject are bad, what percentage of reject are good. Are you aware of this technique, or shall I go in more deep?
Sir, like I have one question here. Like, if we have a through the door population, and we have the accept and reject population on the basis of some cutoff. So you are saying that the accepted population has known good and known bad only. And what about the reject who have been rejected by us, but whose let's say we have the bureau performance. So we would ideally want to include them also. So we take those set for which we have the bureau history and include them in our analysis and rebuild the scorecard.
That is
But-
very easy to do it. That is very easy to do because you have the actual performance. But in case you don't have the bureau data,
So then we have to predict for them.
yes.
Okay.
So in that situation, you will take a ratio. One way is like you set a hard cutoff. Below this probability, they are good. Above this probability, they are bad. And you basically mix them with the good, bad, and make a model. In parceling, you take a ratio of bad and good, and with this ratio, you will multiply by some number, random number, between 3 to 8, because you assume that bad rate cannot be same in accepted sample and rejected sample. It will be 3 to 8 times. For instance, look here. You have this many customers. These are bad, these are good. This is bad rate. Bad rate means 4 divided by this value, 0.06. And you are saying that bad rate of accepted is this, and it is 3 times for the rejected customer. When you say rejected customer has 3 times rate, you multiply this value by 3 and you get this. You multiply this value by 3 and you get this. And then you multiply, these are your rejected count. The rejected count, you will multiply this, you'll get number of bad customer, which is 5. You multiply this value by this, you'll get number of customer bad, which are 21. You subtract from this value, you'll get good customer. Are you following? This is what we have implemented in our code. So let me go back to the partially. So bad rate for the reject cannot be same as for the approved. So you will allocate higher number of bad from the reject. And its number is like, it can be between 2 to 8 times. We have taken 3. Very simple and very controllable. You assume that reject are more riskier than approved. Then you have fuzzy augmentation. In fuzzy augmentation, you make a good bad model. Then you score the rejected, and then you assign weight to each customer who have been scored based on the probability. So, for instance, if probability is 0.3 of being good, being probability of default is 0.3, then you say 0.3 is weight, and then you assign default value as 1. 0.7, 1 minus 0.3 is 0.7, you will assign value as 0. So you will create two observations from each observation to do the fuzzy augmentation. Is this okay? For reject inference verification, you will compare the bad rate of known with the bad rate of the inferred. Normally, bad rate of reject should be 2 to 8 times the bad rate of the approved. And you need to review the bad rate or weight of evidence of pre versus post inference. We have created fake reject to test the best method for each product. These are different metrics or benchmarking, like AUC should be greater than 70%, so behavior should be 75, KS should be greater than 0.3, IV should be greater than 0.03, correlation should be less than 0.7, CSI should be less than 0.1, PSI should be less than 0.25, accuracy should be greater than 70%, depth should be 3 to 4. So I have finished reject inference. I'll show you how it's being implemented in the code. Are you guys with me?
Sir, I have one question on the bad rate. Must be 3 to 8 times, 2 to 8 times that of. So is it that the first scorecard, whatever the bad rate is coming, and from the second scorecard, whatever, like after the augmentation, the scorecard that we are getting, that overall bad rate must be higher?
No, not overall. Which means if you look at this slide here, my bad rate is 0.06. Here my bad rate is 0.017, which is 3 times.
So, sir, like for each decile, we need to ensure that it is 3 to 8 times.
Yes.
Okay, but I think the line on the PPT said the bad rate of the approved, 3 to 8 times the bad rate of the approved.
This is approved bad rate. This is rejected bad rate. So if you choose 3, you multiply by 3 to each column, and then allocate rejected bad and rejected good.
Like the only confusion I'm having is that this rejected bad rate, is it the bad rate from the new scorecard or only for the inferred population? This is the bad rate.
For the infant population.
Okay, like you have not, like we are not combining the old population, known good bad also with the inferred and then coming out with the bad rate.
Thing
It's
is,
not.
this is bad and good. This is inferred bad and inferred good. You will combine these two. You will combine these two. I'll show you how it's done.
Okay.
So we have copy of rejected data which we have created. Then we see all the variables which are there here. In the rejected data. It will have missing the event variable, other variable 45. So we do the missing value treatment with the same values with which we did the training data. After that, we will check the missing here again. Here we have missing here, this one. But after we did the missing value treatment, we will check again here. Only these two have missing values. Rest all is sorted. So after doing the missing value treatment, we will do the outlier treatment with the same value. We have taken the backup of this. To do the outlier treatment with the same value. Once we do the outlier treatment and missing value treatment for the rejected sample, we will check again the graph. Graphs are coming okay. Again we put it back there. And then we will do the WOE transformation of the rejected sample using the same data. So once we do the WOE transformation of the rejected data in the same value, we will get these many values here extra. We see the columns here. And we will create another data set where we keep the only our original data. In another case, we will put the new variables. These are new variables. Now we will assign the probability to the rejected data using this particular function, which means assigning probability here to the training, assigning probability to here to the rejected. Okay. Now look at both of the data. So you have probability score here. Look at the describe, look at the rejected data. You will have score here, probability here. So based on this probability, we will create a table like this one. We describe so we identified the quantile for this particular data and we put it here. So after we divide this into quantile, it will look like this one. These are bins. This is quantile. And we will do some more analysis like to get into this format. We got this table, which is half of this table. So it has bad rate, good, bad, total, mean score, mean probability, quantile. Okay. Are you guys following? Again, we will do some backup here and then we will divide this into using the same bins which we created here. We will divide into those bins. So based on those bins, we got this kind of calculation. Okay, this was what one. And then we will calculate. You see this particular one. This is bad rate of training. This is bad rate of rejected. This is 3 times. So we run this code. So bad rate is 0.05, 0.15, 0.56, 0.168. If you multiply this by this, you'll get the rejected bad. This is inferred bad. So once these inferred bads are there, you want to merge them with the total data. For that, I have written this. This particular output is in the parseling. Here, this code will do merge of rejected with the accepted one. This code. And we'll see what is the status afterwards. So we have 779 event in this data. After you sum this one, parseling output. Sum this up. 779, right? Can you guys hear me? So we have 779 rejected beds, which are inferred. And we created a data set here, where it is 779 events in this data. And this data set is created for rejected one. Let's say describe. So we have 5182 count. This is mean. We will drop the NA if there is a NA here. There's no any here. And this is head of the rejected.
So how did we get the bins for the known good bad which we used for rejected also?
Thing is 1 minute. Bins here. What I had done here is I had run this code with Qcut first. After running with the Qcut, I got the bins which are 12 in numbers.
Yes,
And
sir.
I-
Like, if we made only till 10, then is it possible that the probabilities of default deciles would not have been reached 1?
No, it should be all right, but at the moment I can't change the code because I have to redo everything. But you can put 10 here and redo the analysis.
Okay, okay.
Yeah. We are here and we basically have done this and we basically push this to the point head. Now we make copy of this here and enter this value of rejected, this particular thing in this data, which is our rejected data. Let's do it. We put it in the another places. So if you look at the columns here, these columns, if you look at the columns here, they should be similar. Then only you can merge these two data sets. It has 10, 39, this many values. It should have 779. And it will have, this is our old one. But once we merge this one with this, you'll get the data set for the application. This data set is here. This is the data set. This is your data set with reject inference. Is this okay? If you want to ask question, I can explain you the logic, but you have the code. Anybody want to ask any question? You have to do it yourself to understand it more, because reject inference data has been merged from here to here with the information of bad. So this is one part. Then another part is looking at the application scorecard.
So one question I have on the choice of the multiplier that you are choosing between 2 to 8, like it's a huge range. So how do like someone decide, because we are fixing it for ourselves only, like in the code that it should be 3 times.
This information should come from the management.
Okay.
Like how you want to treat customer which are rejected. Do you want to treat them very risky? You will put 7. Do you want to treat them less risky? You will put 2. Do you want to put them Medicare? Then you put 5. So it will come from the management.
But sir, like on what basis they will decide, because they don't have their performance, and those are already rejected.
One idea is like you choose 10 customer, get the 10 customer data from the bureau. After getting the 10 customer data from the bureau, you see how many have defaulted in your data and how many have defaulted in their data. So you can find a ratio by comparing the training data with the bureau data. That is one way. Second way is you ask the finance department what they think about this customer. Are they very risky or less risky or risky?
But like sir, for those whose even bureau data is not available, then how can they decide?
In that case, you have to basically ask finance department or you check with the economy. So there will be multiple factors based on that they will tell you this factor should be used. You don't have to worry about which factor should be used. They will tell you. Like I was telling, they will tell you cost of a good customer, so profit from the good customer, loss from the bad customer. Same way, they will give this number to you.
Okay, sir. Thank you.
So we have to follow exactly same step which we follow for making the behavior scorecard, load the data, check for the missing values, and then these are the columns. Divide the sample into 30/70. After dividing sample, do the region mapping, which we did. We do the missing value treatment. After doing missing value treatment on this one, we do the same thing with the validation data. Do the missing value treatment. After doing missing value treatment, do the outlier treatment on the training data. After doing the outlier treatment on training data, see the all variables here. Then you have validation data. On validation also you do the outlier treatment. Once that is done, then you do the segmentation. In this case, we have arrear month as a 0.02 as a segment. So neither this segment is fit, neither this segment is fit because there are less than 200 events here. These two segments are okay. So we do the same analysis here, which we did in the behavior scorecard, creating two segments and making one model on this one. Here we got 58%, which is not acceptable. You will immediately reject that particular segment. The 65, and then you pick the model here, you got 61. So it's not great results, but you are not happy with what you're getting from this one, this segment, in terms of the score. So you decided to build the scorecard on the complete data. So making the scorecard on the complete data, you will start with the same steps which we did in the behavior scorecard. Exactly same step. Correlation analysis. The correlation analysis, you see which variable need to drop. Like you are going to drop this one, you drop this two. And then after dropping these variables, you will see the correlation heat map. This is coming properly. And then you do the WOE analysis on the model. After doing WOE analysis, you figure out TC utility is behaving very well this time, 0.66. So So you will keep this one CC util, and you will get the all variable here in the decreasing order of IV, and you select, you do the plot of the WOE. After doing the plot of WOE, you will see which variables are good here, like this one. This is okay. This is also okay. This is okay. This is okay. This is okay. Most of the variables are okay. Only one variable or two variable has been dropped, which is employee length and number of CCG. These are dropped. Rest of them been kept, and this also has been dropped because of some. So we are following exactly same process. And then we are doing the correlation heat map. The correlation heat map, we are saying that everything less than 70 percentile, 70 percentage. After doing the correlation analysis, we come up with these many variables. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 variables. And we do the WOE transformation of the training data for these variables. And when you do the, after doing this one, you look at the heat map. Heat map shows all the variables are okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 variables. Do the same transformation of the validation data set. And then you run the logistic regression. Logistic regression. And you get your all the coefficients here. Your ROC is coming 70% approximately. Accuracy is 74. And the application is scorecard. So we have followed exactly same step which we have followed in the behavior scorecard, and we reached to this result. And we have implemented SMOTE also because we wanted to improve the results. So after improving the SMOTE, we got AUC of 69.9, which is very close to this one. We did not change to this data set. So we got ROC here. ROC here is like 69.9. We got gain curve. We got confusion matrix. And we got the score, which is look like this one. This is how final scorecard looks like for the application. We plotted the lift curve here, plotted the cutoff. Cutoff is 0.567. In the case of behavior scorecard, it was 0.511. Is 0.567. And then we have strategy curve. Then we have profit curve. Then we have KS, which is 0.67 again. The cutoff to the first KS. And our approval rate is improved to 80%, and KS cutoff has gone to 528, which means application scorecard has better optimal cutoff compared to what we have for the behavior scorecard. It was 611. It was 77 here. I have all the result in the presentation also. So we have the behavior scorecard for the application. This is application scorecard. Look here. Application scorecard is this one. This is application scorecard. This is util error status. This is a scores. Anybody, any question? We need to follow the same process to build the application scorecard. PSI is 0.14. Then CSI calculation, these are CSI calculation. Everything I have put here and I'll show it to you. So this is segmentation. Segmentation is happening on arrears month. This is information value for the application scorecard. And these are variable selections. This is correlation heat map. This is model performance, 69% AOC, which is close to 70. This is with the SMOTE. This is again close to 70. This is ROC. Cutoff is 0.567, 0.567, 0.567 with the KS also. Anybody want to ask any question?
What exactly this strategy curve refers? This
It's a map.
strategy.
It maps between. It's a curve between acceptance rate and bad rate. It comes from the gain chart.
Okay, from the gain chart.
Yeah.
Okay.
This is profit curve. This is confusion matrix for the application scorecard. And this is our score graph. Most of the customers are non-default. So we have this kind of shape of the score. This is lift chart. Lift has been reduced. It was 5 for the behavior scorecard, but has gone to 4. This is our gain table from which we plot the strategy curve. This is PSI, it's 0.14. This is CSI. So guys, you need to build the scorecard on this data as exercise. This data will come from the output of this. Anybody want to ask any question? Because my presentation is over, code is also over.
So I just had one question on the error rate, the like the type 1 error. So I want to ask that like if we are getting an because accuracy ratio and the misclassification error are sum up to 1. So if we go by the thresholds, then let's say the error rate is coming out to be 30%. So, like, what is the remedy in such situations? Like, if there is a high error rate in the model.
If there is a high error rate, in that situation, you need to adjust the cutoff. That is one strategy which will minimize the error rate. If your model is made in a such a way that optimal cutoff is giving you that result, in that situation, you need to think about whether you need to rebuild the model or you need to do some more tweak with the model so that error rate is reduced. Because more error rate you have, more problem you have as far as fraud management is concerned, as far as the medical field is concerned, because you want to use the optimal cutoff in those fields.
So, like, sir, even for lending decisions, it is a serious issue if we have a very high error rate.
It's not possible to have high error rate and build a scorecard. If your scorecard is not working, then you will have high error rate. In that case, you need to rebuild the scorecard.
So, sir, like an error rate of 30% for type 1 error would be high, very high enough.
Yes, it will be high. Thing is, you want to stick to as far as I was showing you something called accuracy report. You want to make sure that you're getting this kind of, these are expected things. You should get this kind of thing here also. Then your error rate will go down. If this is not happening with this report, then management needs to be concerned.
So, sir, like if there is a falling trend only with the rise in scores as shown here, like it is going from 18% to 4, it's a continuous fall, and that is what we want also. But still, like in both the cases, the actual bad rate percentage and the expected bad rate that we are getting from the model, there is no like a trend break, there is a continuous fall only. But still, if we have a high error rate, then what could it imply?
It will employ that you need to rebuild the model.
Okay. Because then we look at from say that the parameters maybe they are not selected as or they are not that good or something.
It's not just parameter. It could be data is not good. You are as good as your data. In my case, like when I was building this model, data was good. I could build a good model despite making so many compromise. Like I did not do the attribute grouping. Despite that model came good because data was good. But if data is not good, in that case, model will not come good. If data is a issue, then you need to play around with the cutoff, how to minimize the error rate. If that is not also working, then you need to use the existing replacement scorecard which gives less error. If that is also not possible, then you need to rebuild the scorecard with the new data. Because the reason for this kind of problem is error rate. It cannot be built with the error rate which is 30%. It has to build in such a way error rate is lesser. But if data has changed, this profile has changed, in that case, error rate will be more. If
So,
this,
like, let's say, sir, it's a development only, not a validation. So, if it's development, first time we are building, and if we are getting a high error rate or a low accuracy from the confusion matrix at the threshold, then we should try to rebuild the model.
yes,
Okay. And sir, one more thing I've noticed that if we're handling the imbalanced data set, like you showed yesterday, the balanced class weight and the SMOTE. So sometimes what happens is that when we handle the imbalance, the Gini gets lower. Like I have sometimes I found ki when handling imbalance, because this is a like pervasive issue with the default data set, ki the defaults are always low as compared to the non defaults. So if we handle the imbalance, sometimes I get low accuracy. So like is it
Actually, what you say happens is other way. When you have balanced data set, accuracy get improved, Gini also get improved. Because when I was building this model, I was looking to do the oversampling. To do the oversampling, I had to figure out how to do it. Then I checked on internet the code and I did the oversampling. Initially, I was getting results like 60%. Then my result improved to 78%.
like, sir, I tried recently only once this imbalance, because in this decision tree model, sir, there is also parameter known as sample underscore POS underscore weight, which also handles imbalance. And once I specified that, so the my accuracy came out to be lower. So I was just wondering, ki, is it a very important step to do? If
Thing is, if you are getting better results without oversampling, I think better way to go about without oversampling.
like handling imbalances, then not of so criticality if we are getting higher accuracy without it only.
Exactly.
Okay. Okay, sir. Thank you.
More questions? Anybody want to ask any other question? Please ask.
Uh, yes, Nitin. So, I just wanted to, ask that, in reject influencing concept, what to do if, the persons we reject the most, at least, 50% or 20% of them are, due to bank, and they do not have, the appropriate, variables that, we want, how would we
Thing is, once you work with the reject data and you combine it with the original data with a known good bad, after that you need to build the model again from the scratch. So process need to be repeated. You cannot go back and use the analysis which you had done for the known good and bad. So you need to do the everything from the scratch. Other thing is what is the good ratio between known good bad rate and rejected bad rate? It will be subjective. It will totally depend on the organization how they treat the rejected customer. How urgently they want rejected customer to come and join them.
Yeah, yes, because the new to bank will be like kind of a thin file, like they don't have any information yet. So I guess the most of the valuable the most important features that that can predict the bad customer more accurately won't be there itself, right? So
I really can't say like how accurately they can predict because that is subjective decision of the organization. Organization decide how they want to treat the bad customers because some organizations when they build the model and they have very less rejected customer, they will treat them as a bad customer and make a model. Sometimes they do that.
okay, yeah, got it.
Yeah. Any other question? Anybody else?